Let's get started with today's lecture. So when we last left off, we were talking a lot about balancing acid-base neutralization equations. So these are some tricks to balance chemical equations. So fundamentally, the key to understanding acid-base reactions is you have an H+ source reacting with an hydroxide source to yield water, okay? So this is the backbone of all of our acid-base reactions. These two ions always react in a 1-to-1 ratio to form water. So we adjust our coefficients so our H+ equivalents match the OH equivalents. So let's look at an example. So looking at hydrochloric acid, which is a strong acid, my question to all of you is, how many H+ equivalents do we have? How many H+ equivalents do we have? And don't be shy to type in the chat. How many H pluses? Yep, exactly right. So we have one H+ equivalent. Now looking at hydroxide, sodium hydroxide, how many hydroxide equivalents do we have? How many hydroxide equivalents do we have? Also one. So then, is this a 1-to-1 ratio? Do we have the same amount of H+ and OH minus? Do we have the same amount of H+ and OH minus equivalents? Yes. Yep. So we put a check mark. This equation is balanced as written. Okay, let's do another example. Let's look at sulfuric acid. How many H+ equivalents are in sulfuric acid? How many H pluses do we have? 2, exactly right. So we have 2 H+. And then for potassium hydroxide, we have 1 OH minus, 1 hydroxide equivalent. So then, in order for our H+ and OH minus equivalents to match, what do I need to multiply my moles of potassium hydroxide by? What do I need to multiply it by? 2. Exactly right. So now we have 2 OH minus and they cancel out. Another trick is if you look at the salt and we know that we have 2 potassiums in our salt, we also need 2 potassiums from potassium hydroxide. Now we still have to balance water. Remember how we said the equation is H+ plus OH minus leads to water? So if we have 2 H+ and 2 OH minus, my question to all of you is, how many water molecules will we make? How many water molecules will we make? And don't be shy to type in the chat. 2, exactly right. So we need a 2 in front of water. This is a shortcut method. It's another way of handling and balancing acid-base reactions. Let's look at another example and let's try to do this one a little bit faster. So in phosphoric acid, how many H+ equivalents do we have in phosphoric acid? 3. So we have 3 H+, and potassium hydroxide just has 1 hydroxide equivalent. So then, what do I need to multiply my coefficient for potassium hydroxide by? 3, exactly right. So that gives us 3 hydroxide, so we put a 3 in front. And if we have 3 H+ and 3 OH, how many waters are we making? How many waters are we making? 3, exactly right. So this is a nice trick to balance acid-base reactions efficiently. Let's do one more just to drive this point home. In HCl, we already established it as 1 H+ equivalent. And looking at calcium hydroxide, how many hydroxide equivalents do we have? How many hydroxide equivalents? 2. Okay. So then what has to happen to our coefficient in front of HCl? What do we have to multiply our coefficient by? 2. Okay, and how many water molecules do we make? 2, exactly right. Perfect. So this is a nice trick for balancing acid-base reactions. So let's take a look and let's try a few exercises where we try to predict the products of the following reaction, and let's try to write a balanced chemical equation for each reaction. So this is where we're going from words to an actual chemical equation. So we have a solution of sodium phosphate and sulfuric acid are mixed, okay? So let's write out our formulas first and foremost. So what's the formula of sodium phosphate? What's the formula of sodium phosphate? Yep. Na3PO4, because we take Na plus and we cross it with PO4 3 minus. When we cross the charges, we get Na3PO4. It's reacting with sulfuric acid, which is H2SO4. Okay. And now this is another trick that we're going to use. So in acid-base reactions, we generate a salt plus a conjugate acid, okay? And let's rewrite the salt in a way that we can visualize this. We generate a conjugate base and a conjugate acid. So just thinking through, what is the conjugate base? What is the conjugate base of sulfuric acid? What happens if we get rid of all the protons on sulfuric acid? What's the conjugate base of sulfuric acid? What's the formula of sulfuric acid if it loses all of its protons? So if I just take H2SO4 and I dissociate it to H plus, what's the other ion that we get? Yeah, sulfate, exactly right. Okay. So this is our first acid equation to consider. So sulfuric acid is going to react to make sulfate. Okay. And what is the conjugate acid? What is the conjugate acid of sodium phosphate? So if we have sodium phosphate, what conjugate acid will it make? So if we have phosphate anion, what is its conjugate acid? So what happens when it gains protons? So when our conjugate acid gains protons, what are we going to make? What is the conjugate acid of the phosphate anion? Yep, phosphoric acid, exactly right. And how many protons do we need to gain in this process? How many protons do we need to gain? 3, exactly right. Okay. So now that I have my two acid-base equations, what I'm going to do is I'm going to find the least common multiple. So I have 2H plus on top, 3H plus on the bottom. What's the least common multiple between 2 and 3? What's the least common multiple between 2 and 3? 6. So I'm going to multiply my top equation by 3, my bottom equation by 2. So I have 2 sulfuric acid leading, whoops, sorry about that. I have 3 sulfuric acid leading to 3 sulfate and 2 phosphoric acid produced from 2 sodium sulfate. Okay, and now just to complete this equation, how many sodium ions do we need on the right-hand side? How many sodium ions are we making? So what's 2 times 3? How many sodium ions are we making? 6. Okay. And we're just going to combine our sodium and sulfate to write this as 3 sodium sulfate. There we go. So I call this the quote unquote half reaction method of balancing acid-base reactions. An equation to generate your conjugate base and conjugate acid, you count the number of protons and then you balance the number of protons on each side. Does this method make sense? Does this method look familiar to other methods that we've utilized in this class? And again, just as a reminder, the formula of this is really key. So remember, the salt contains the conjugate base. So if you can figure out the formula of the salt, you can actually use it to generate the rest of the equation. Is everyone comfortable with this method? Let's try a few more examples and let's see how this can work. So we have lead carbonate added to a solution of sulfuric acid. So we have PbCO3 plus H2SO4, and we're trying to predict the products of this reaction. Okay, so let's play a game now. So I'd like you to tell me, what is our basic species? What is our base in this reaction? What is our base? What is our anionic species? What is our anionic species? Yep, exactly right. Okay. And what conjugate acid will we be making? Or what fully protonated species will we be making? How many protons can carbonate pick up? So carbonate is CO3 2-, so it can pick up how many protons? 2, exactly right. And we make H2CO3 plus lead 2+. Okay. Now, if we look at this H2CO3, is carbonic acid very stable? Does carbonic acid stick around for very long? Is carbonic acid stable? No. So then we're going to rewrite our equation. And this time, what do we break our carbonic acid into? What do we break our carbonic acid into? What does carbonic acid break into? Not the lead carbonate, this carbonic acid, this H2CO3. What does it decompose into? You typically see bubbles in this reaction. Think like baking soda and vinegar. So that's an acid dissociation, but just as a reminder, carbonic acid decomposes to yield water and carbon dioxide. Okay, so we have our first quote unquote half reaction. Now let's repeat this process for sulfuric acid. So sulfuric acid is going to react to generate what conjugate base? So what's the conjugate base? What's the fully deprotonated species from sulfuric acid? What's the fully deprotonated species from sulfuric acid? So what does sulfuric acid make? What anion does sulfuric acid dissociate into? Sulfate, yep. And how many H plus equivalents? How many H pluses do we make as well? 2. Perfect. So now we have the same number of H pluses on each side. So we just add them together and our equation cancels. And we're left with water, carbon dioxide, lead 2 plus, and sulfate. And we can write our lead 2 plus and sulfate. We can combine our lead 2 plus and sulfate and just write lead sulfate. Oh, 2 minus, sorry. There we go. The tablet caught an additional, the tablet sometimes catches an additional pen stroke on accident. Yep, it's SO4 2 minus, yep. So does this acid-base, quote unquote, half reaction method make sense to everyone? Does everyone understand the logic behind this method? The reason why I like it, it's an easy way of predicting products, and it really helps you visualize the proton transfer between your acid and your base. Are there any questions on this method? Really don't be shy to ask. This is a new method that I thought up, I think, last semester, because it really helps in developing a skill set that will need to handle redox reactions. You can still balance it like usual. As long as you're able to efficiently predict the products. The reason why I like this method is it makes it very clear the process for predicting products. But yes, you're more than welcome to balance it like usual. This is just another tool in your toolkit to predict products and balance equations. Does that make sense? Whatever method gets you to the correct answer is, I just like showing a range of different tools, and whatever a student prefers to use, that's perfect. Okay, let's look at a few more examples. So I'd like you to start with question 1. So we're going to spend about 6 minutes on this question. I'd like you to predict the products of each of the following reactions and write a balanced chemical equation for each reaction. Now, in order to make sure that we're all on the same page, we're going to start by writing the formulas of our reactants. So when we say potassium carbonate, what formula are we referring to? Drawing from our nomenclature experience. When we say potassium carbonate, what are we referring to? What formula? Yep. Okay. And when we refer to nitric acid, what's the formula of nitric acid? And if you need to review nomenclature, it's present in chapters 3 and 4 of the notes. So for nitric acid, would someone like to volunteer a formula? HNO3, exactly right. So remember, nitric acid is derived from nitrate, which is NO3 minus. We cross it with H plus, it's 1 to 1. Okay, with this equation established, I'd like you to predict the products. So just to give you a hint, there are 3 products from this reaction, and I'd like you to message me in chat what you predict the 3 products are and their coefficients. If you want, you can even type a full balanced equation into chat. But I'd like you just to take a moment and to try and predict the products and then balance this equation. And don't be shy to message me with questions in the chat. But I want to give everyone about 45 minutes to try and work through this problem. This is very similar to types of questions you'll see on exam 3. So I want us to build this skill. Very, very, very close. You're on the right track. Just think a little. Apologies for the temporary disconnection. My internet intermittently shut out. There's been internet disruptions in the Hemet area, so I apologize for that. I'll be checking chat. Does anyone have any proposed solutions for our products and the coefficients? Perfect, perfect. Let's get a few more responses in the chat, and then we'll be able to discuss this problem. And try to balance the left-hand side of the equation as well. And we'll spend about 2 more minutes on this problem. Perfect, perfect. So we have a proposal for a complete balanced equation. So let's take a look at this problem now. So first things first, I like to write out my base. So we have our potassium carbonate. And my question to all of you is, what is the conjugate acid? What is the fully protonated form of potassium carbonate? What's the fully protonated form of potassium carbonate? Would someone like to propose in the chat, what's our fully protonated form of potassium carbonate? Or what is the acid form? What is the fully protonated form or conjugate acid of carbonate anion? And don't be shy to type in the chat. So what happens if we fully protonate our carbonate anion, which is CO3 2-? What species will we generate? What acid will we generate from carbonate? Carbonic acid, exactly right. Okay, and how many H+ equivalents will that require? How many hydrogens do we need to pick up? How many? 2, exactly. Now let's look at nitric acid. So nitric acid, what is the conjugate base of nitric acid? What happens when nitric acid loses all of its protons? What happens when nitric acid gives away all of its protons? What do we get? Nitrate, exactly right. And how many H+ equivalents have we thrown away? As we can see, just by balancing our number of atoms, we threw away 1 equivalent of H+. Now we look for the least common multiple. So what's the least common multiple between 1 and 2? What's the least common multiple between 1 and 2? 2. So we're going to multiply our bottom equation by 2 and our top equation by 1. So we have 2 nitric acid leading to 2 potassium plus 2 nitrate plus, and now when we look at our carbonic acid, what do we break our carbonic acid into? What 2 species do we break our carbonic acid into? Remember when we saw carbonic acid last time, what does it decompose into? CO2 and water. Perfect, perfect. And now just to finish off this problem, we're going to combine our potassium and nitrate to write 2 potassium nitrate. Okay, this is one method of doing things, but the other method that I like to use, is the salt-based method. Okay? So we identify our cation and we identify the conjugate base. And all I do is I take my cation and I cross it with my conjugate base. And if I have 2 potassium plus, in order for me to make a complete balanced amount of salt molecules, I just need to adjust the coefficient of all species that have my conjugate base. So you can get the same result using the salt method, but I personally like the half reaction method because it's very easy to see where each of your products are coming from, and it makes it easy to check your work. But whatever method you work or you use, you're more than welcome to. Okay, let's keep going and let's take a look at the following example. So copper 2 sulfide is added to a solution of hydrochloric acid. So I'm going to need your help now once again. Let's try to write some formulas. So for copper 2 sulfide, would someone like to tell me the formula for copper 2 sulfide? So this is nomenclature practice. You're gonna have to develop those nomenclature skills. CuS. So copper 2, the 2 signifies the charge. Sulfide is S2 minus. We cross our charges and we get CuS. Okay, hydrochloric acid is just HCl. And then I'd like you to predict the 2 products from this reaction. Keeping in mind, if you want to use the salt method, our cation in this case is copper 2 plus. and our conjugate base is something that you're going to have to fill in. You're going to have to figure that one out if you want to use the salt-based method, or you could use the half reaction method. Whatever gets the job done. So let's take about 3 to 4 minutes, and you're more than welcome to message me with the balanced equation products from this reaction. And I have them labeled for A and B, or you can just message me the entire balanced equation. Whatever you're comfortable with. Yep, Mariana, that looks good. And don't be shy to message me. I'll be more than happy to give feedback. Hiral, your predicted products are perfectly correct. All you need to do now is adjust your coefficients. Let's get a few more responses in the chat, and then we'll discuss in about a minute and a half. Okay, so let's discuss this problem. So our first order of business, what is our conjugate base? What is our conjugate base in this reaction? What is our conjugate base? Yep, chloride. So if we want to use the salt method, we take our cation, which is copper 2+, and we cross it with our anion. So we predict a salt of copper chloride. Okay. In terms of our acid, we take our base and H+. So we have H+ and S2-. We cross our charges, we get H2S. Now, all we have to do is balance our atoms. We have 2 chlorides on the right, so we need 2 chlorides on the left. So this first method is the salt method. It's serviceable for sure. It works, it gets the job done, especially for these simple equations. Let's look at the half reaction method. So from the half reaction method, so copper sulfide is going to react to make hydrosulfuric acid and copper 2+. We need to gain 2 protons to complete this process. Hydrochloric acid will dissociate into H+ and Cl-. If I want to take the least common multiple, the least common multiple is 2, so I multiply my bottom equation by 2. H+ cancels, we get the same result. Again, whatever method you prefer, both are valid. It really comes down to preference. Do these examples make sense to everyone? Is everyone more comfortable predicting the products of acid-base reactions? This is more than just balancing equations. This is more as a tool to predict the products of reactions and then balance the equation for acid-base reactions. Yep. And this method is unique for acid-base reactions. But yes, this is essentially another way of balancing equations, but the utility of it is it gives you insight into the products. And that's the main draw, that you can have a better sense of what products you're generating from the reaction. Another trick if you're so inclined is all you have to do is take your two anions and then swap your anions. That's another quick trick to figure out your products. There are endless ways to predict products and balance equations, but I think we have a fair amount in your toolkit. And if you find another one that you're comfortable with, don't be shy to use that. Any other questions? Is everyone comfortable with this idea? Well, if I don't see any other questions, let's just keep going and let's talk about unique types of solutions now called buffer solutions. For those of you who are in biology, buffer solutions are really important because they control the pH. They're used for cell culture. They're used for certain biological assays where you're detecting the presence of certain small molecules in a sample. So you're often going to, if you're in biology, you're often going to end up having to make buffers. So a buffer solution is a solution containing a mixture of a weak acid and its conjugate base. And just to be 100% clear, the conjugate base in the strictest definition, the correct definition, is only different by one proton. Now, a buffer is a solution that resists significant changes in pH upon addition of either acid or base. So an example of a buffer that we use every single day, our blood is a buffer. It controls changes in pH. So buffers resist changes in pH. One, the conjugate base in the buffer solution reacts with strong acid to generate a weak acid. So for example, if you have a buffer solution of sodium dihydrogen phosphate and you add some hydrochloric acid to it, let's do sodium hydrogen phosphate, and you add some hydrochloric acid to it, you'll generate sodium dihydrogen phosphate and sodium chloride. So in effect, what our buffer has done is we've taken a strong acid and converted it to a weak acid. So we minimize the effect of this strong acid on pH by reacting and converting it into a weak acid. Likewise, the weak acid in the buffer solution reacts with strong bases to generate a weak conjugate base. So for example, if you have a sodium hydrogen sulfate buffer system and you add some hydroxide, let's pretend we're adding some sodium hydroxide. The buffer will react with our strong base to make sodium sulfate, which is a weak base, if you can even call it that, as well as some water. So buffers work by converting strong acids and bases to weak conjugate acids and bases. Does that make sense? Is everyone comfortable with this idea? So as we generate a weak acid and weak base from strong acids and strong bases, the pH does not change substantially when you add acid or base to a buffer solution. Okay, so we'll often see this buffering effect when we start to talk about acid-base titrations, which is the next bulk of our discussion today. So titration fundamentally is using a standard solution of defined known concentration to determine the concentration of a solution of unknown concentration. So titration utilizes stoichiometry in the chemical equation to relate the quantities of known stock solution and unknown solution. So for acid-base reactions, we use fundamentally the building block acid-base reaction. So we have acid and base. Our acid transfers a proton to our base. So our acid reacts to make the conjugate base. Our base reacts to make the conjugate acid. Now, we call the equivalence point the point when both reagents are present in their stoichiometric ratio given by the chemical equation. Okay? It's not equal amounts, it's stoichiometric amounts. So for example, the moles of acid equal the moles of base times our stoichiometric ratio. So essentially, the acid and base will react completely with no excess reagent. So let's do an example. So looking at the following reaction, the moles of sulfuric acid, so at the equivalence point, the moles of sulfuric acid would be equal to the moles of sodium hydroxide. And now this is where things get interesting. How many, let me rewrite this. So at the equivalence point, my question to all of you is, how many moles of sulfuric acid react with how many moles of sodium hydroxide? What is our stoichiometric ratio for this chemical equation? What is our stoichiometry between sulfuric acid and sodium hydroxide? Let's get a few more responses in the chat. 1 to 2, exactly right. I see a lot of reasonable responses to that effect. So this is our equivalence point, when the moles of sulfuric acid are present in stoichiometric amounts relative to sodium hydroxide. So the key takeaway, I want you to keep this in mind, you always need a chemical equation when you're dealing with a titration. Full stop. This mole to mole ratio, this stoichiometric ratio, comes from our chemical equation. Okay, let's keep going. So we often handle acids and bases as solutions. So we can figure out moles by taking molarity times volume. So substituting, this is a textbook titration equation. The molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of base. Remember, this is just referring to moles of acid and moles of base. And this ratio is our stoichiometric ratio. The reason why we wrote this in terms of volume is because we often handle acids and bases as solutions. We don't handle neat 100% pure hydrochloric acid because that would be a little difficult since it's a gas. Okay, so the key thing I want you to keep in mind is titrations only look at the volume of acid or base solution dispensed to calculate the moles of acid and base. The total volume of the solution or the added water does not matter, right? Do we see any volume of water in this equation? Do we see anything that cares about the total volume of the solution? No, we only care about how much acid and how much base we've added. That's it. And that's the beauty of it, since titration is a relatively robust technique. Okay, so it's difficult to detect the moles of acid and base in solution. We can't just physically stare at a flask and say, oh, there's 0.3 millimoles of acid still remaining. Instead, we detect the concentration of H+ or hydroxide using a pH indicator. So an indicator is a chemical compound that changes color in response to changes in pH. So this is your good old friend phenolphthalein. And these are two other indicators that you'll see in Chem 102, methylene blue and methyl red. So as you notice, as the pH changes, you observe distinct color changes. So we call the point at which the indicator changes color is the end point, which occurs when a slight excess of acid or base is present. This poor student likely messed up their titration. This is way too pink, but nonetheless, this is an example of an end point when the indicator changes color. Okay, so we like to describe pH using titration curves. They show pH as a function of the volume of acid or base added. So for a strong acid, strong base titration, let's look at an example of a titration curve. So initially we start with our strong acid. Oh, whoops. Sorry about that. So we're titrating a strong base with a strong acid. So initially in our solution right here, we have our sodium hydroxide, which is our strong base, which would mean we have a pH much greater than 7. So as we inch along in this curve, as we move across this curve, we are adding hydrochloric acid. Okay, so as we add our hydrochloric acid, in this first part of this curve, we still have a large amount of sodium hydroxide. Now, as we get really close to the equivalence point, our concentration of sodium hydroxide drops and our pH in turn drops. Okay. Now at the equivalence point, so at the equivalence point, which I have with that circle, so at pH equals to 7, our moles of HCl are equal to our moles of NaOH times 1/1 for our 1-to-1 ratio. And as a result, what is the only species that is present in solution at the equivalence point? At the equivalence point, what's the only thing that we have in solution? What do we have a solution of? Looking at our reaction products, if our hydrochloric acid and sodium hydroxide completely react, if they completely react, what is the product in solution? What is the product that we've made? If hydrochloric acid and sodium hydroxide are an exact stoichiometric ratios, they're 1-to-1. They've completely reacted. So what are we making in this reaction? What do we make? What's the product of this reaction? Water, exactly right. And water has a pH of what? Why is our end point at pH 7? Water has a pH of 7. Does that make sense to everyone? Does this idea make sense? If we react to make water, we'll make a pH 7 solution. Okay. And now, past the equivalence point, so if we keep adding HCl, we now have a solution of HCl. Okay, so this is how to read a titration curve. We call the region when the indicator changes color, the indicator region, and we try to have our indicator region as close to the equivalence point as possible. Okay, so let's do some calculations now. So 10 milliliters of a sodium hydroxide solution of unknown concentration was titrated with a 1 molar solution of hydrochloric acid to the endpoint. The titration required 9 milliliters of HCl to reach the endpoint. We're asked to calculate the concentration of the unknown sodium hydroxide solution. So we're going to start from our basics. So at the equivalence point, the moles of HCl equal the moles of NaOH times 1 mole of HCl per mole of NaOH. We get this from our equation. Now we're going to substitute. The moles of HCl can be thought of as the molarity times the volume. And that's equal to the molarity of sodium hydroxide times the volume of sodium hydroxide times 1/1. Okay, we're now going to rearrange this equation to solve for the molarity of our sodium hydroxide, and we get the molarity of our sodium hydroxide is equal to the molarity of our HCl solution times the volume of our HCl solution divided by the volume of our sodium hydroxide solution times 1/1. May seem redundant, but this stoichiometric ratio is going to come up a lot later. Okay, so now all we have to do is plug in our numbers. The molarity of HCl is 1 molar. The volume of HCl is 9 milliliters, and the volume of NaOH is 10 milliliters. And if we punch that into our calculator, don't even have to. This one you can just do in your head in this case, but you're more than welcome. If we have a tool, there's no problem in using it. We get 0.9 molar because milliliters cancel. And a key thing, you want to make sure that the units cancel. So check your units. Does this example make sense to everyone? Does this titration equation look familiar? Is everyone comfortable with these titration calculations? You don't have to. You only need to make sure that your volumes cancel. If you're doing it stepwise, however, I would convert to liters. But since we're doing it as a one-line solution, you don't have to. Does that make sense? As long as your units cancel for volume, you're fine. But you certainly can convert to liters if you prefer. Okay, let's give everyone a chance to test their own understanding. So we're titrating a strong acid with a strong base. So initially, we have a solution of HCl, which has a pH of less than 7. As we continue to add our sodium hydroxide, eventually we reach a point where the concentration of HCl is low. And eventually we reach our end point at pH 7. Why pH 7? Just as a refresher, what is the product from the reaction of a strong acid and strong base? What is our product? If our acid and base are in stoichiometric ratio, what do we have in solution? Water, exactly. And water has a pH of 7. Okay. Mechanically, this titration is handled just the same as our earlier example. So given that we have 5 milliliters of HCl solution of unknown concentration titrated with a 0.15 molar solution of sodium hydroxide, and that the titration required 4 milliliters of NaOH to reach the end point, I'd like you to calculate the concentration of the unknown HCl solution. So take a moment, given this data, to calculate the concentration of our unknown hydrochloric acid solution. And you're more than welcome to message me with your proposed setup and your proposed solution to this problem. Okay, let's get a few more responses in the chat and then we'll discuss. Okay, I've seen a lot of reasonable solutions. So let's just start from our basic equation. At the equivalence point, the moles of hydrochloric acid would be equal to the moles of sodium hydroxide times 1 mole of hydrochloric acid per every 1 mole of sodium hydroxide. We can then rewrite this in terms of molarity, in that we have the molarity of HCl times the volume of HCl is equal to the molarity of NaOH times the volume of NaOH times 1/1. Perfect. Now we're asked to calculate the concentration of our HCl solution. So we're just going to solve for the concentration of HCl. So the molarity of our hydrochloric acid is equal to the molarity of our sodium hydroxide times the volume of our sodium hydroxide solution over the volume of our hydrochloric acid solution times 1. Now we substitute. Our sodium hydroxide molarity is 0.15 molar. Our volume of sodium hydroxide is 4 mils. And our volume of HCl is 5 mils. Okay, now all we have to do is punch that into our calculator and we get the molarity of HCl is 0.12 molar. Does this make sense to everyone? Is everyone comfortable with this type of problem? Okay, perfect. So let's keep going now. Weak acids and weak bases in titrations. So weak acids generate conjugate bases that are sufficiently basic to change the pH of our equivalence and endpoint. So this acetate ion is basic. So as a result, at our endpoint, our pH will be greater than 7. Okay, it's a subtle change, but it affects what indicator you have to use. Weak bases generate conjugate acids that are sufficiently acidic to change the pH of the equivalence and endpoint. And since our conjugate acid is acidic, our pH will be less than 7 at the end point. Now, there's a special word. So if we compare our base and our conjugate acid, what type of solution, what do we call a solution that's a mixture of an acid and the conjugate base? We talked about these solutions just a while ago. What type of solution, what type of reaction does this look like to everyone? Buffers, exactly right, exactly right. When weak acids and weak bases react, generation of the conjugate acid or base buffers the change in pH. So there is an equation to describe buffer behavior, and if you're in biology or if you ever have to make a buffer solution, this is the go-to equation to describe buffer behavior. It's called the Henderson-Hasselbalch Equation. So it's written as pH is equal to pKa plus log of A minus over HA, where A minus is our conjugate base and HA is our acid. So what this equation does is it describes the pH of a buffer solution as a function of the concentration of the conjugate base and the concentration of the acid. It also allows for the calculation of the pKa of a weak acid and the calculation of the pH of the solution. So it's really good if you want to make a buffer solution of known pH. That's the whole point of this equation. Okay. So when we have a weak acid, strong base titration, so we're titrating a weak acid such as acetic acid. So currently we have a weak acid in solution. Now, as we add our base, we enter what is known as the buffer zone. And in this buffer zone, we have a mixture of our acid, which is acetic acid, and our conjugate base, which is acetate. So this is a buffer mixture. Does everyone notice in this buffer region that is this pH changing a lot or a little? Is the pH changing substantially in this buffer zone? Or is the pH changing very slowly? So I see a lot of people typing that it's changing very slowly, and that's because we have this buffer solution that's resisting changes in pH. Eventually, we approach the equivalence point, and at the equivalence point, we have some acetate in solution, so our pH will be greater than 7. Now, here's the real beauty of this. The math doesn't change. The math doesn't change. But we have some interesting regions that I want you to pay attention to. First of which, if we trace down our graph, this volume is the volume for our equivalence point. Okay? And at half of the equivalence point, so if this is 50 milliliters, at around 25 milliliters, at 1/2 the equivalence, there's a really key feature I want you to know. At the half equivalence point, your pH is equal to the pKa. A buffer means essentially that it resists change in pH. You essentially prevent your pH from changing rapidly. So from the graph, once you find your equivalence point, which is the point of maximum inflection, you can trace and figure out the volume needed to reach the equivalence point, and you can also figure out the volume of the half equivalence point. And if you read the pH from the graph, this pH is equal to the pKa at the half equivalence point. So you can determine the pKa of your acid, which we know is 4.67. Do we see a pKa of around 4.6 graphically at our half equivalence point? Is this dot right here in blue around 4.6? Yep, exactly right. And we'd expect it to take a roughly 50 milliliters to reach the equivalence point. Lo and behold, from our graph, we see a V equivalence of 50 mils. So let's talk a little bit about the buffer zone. So this buffer zone is the region where the acid and conjugate base are present in a 1:10 to 10:1 ratio, and addition of base or acid would result in a minimal change in pH. See the Henderson-Hasselbalch equation to justify that. The half equivalence point is when the acid and conjugate base are present in equal concentrations. So A minus is equal to HA, and in this case, pH is equal to pKa. Okay. So we have all this fancy data, but fundamentally, the only thing that changes for weak acids or weak bases is the pH of the equivalence point. The stoichiometry principles still remain the same. it's still a 1-to-1 ratio, or whatever ratio we choose. It doesn't matter what ratio they're present. The only thing that matters in terms of our calculations is that we account for our stoichiometric ratio and that it's an acid-base reaction. It doesn't matter whether it's a strong or weak acid. The real takeaway I want you to get away from this is you only need to change the indicator. The calculations are the same for a weak acid or weak base titration. So let's showcase that. So let's suppose we have 60 milliliters of acetic acid of unknown concentration, and we titrate it with a 1 molar solution of sodium hydroxide. The titration required 20 mils of sodium hydroxide to reach the end point, and we're asked to calculate the concentration of the unknown sodium hydroxide solution. Okay, so fundamentally, let's write our equation out. Okay, so at the equivalence point, we're going to use our same equation. So the moles of acid, which is acetic acid, are equal to the moles of base, which is sodium hydroxide, times, and now my question to all of you is, how many moles of acetic acid do we have per mole of sodium hydroxide? What is our mole to mole ratio? What is our mole to mole ratio? 1-to-1. Does this equation here look exactly identical to our strong acid titration? Does it look exactly identical to our strong acid titration? Has anything really changed in our calculations? Has anything really changed in terms of the numbers you plug in terms of the mechanics? No, it's exactly the same. So then let's just continue substituting just like we did before. So we'll take the molarity of our acid times the volume of our acid is equal to the molarity of our base times the volume of our base times 1-to-1. Okay, now all we have to do, we're asked to calculate the concentration of our NaOH solution. Oh, this should be acetic acid since we're given the concentration of NaOH. So let's solve for the concentration of our acid. So the molarity of our acid is equal to the molarity of our sodium hydroxide times the volume of our sodium hydroxide over the volume of acid times 1/1. Okay, so then the molarity of our acid, I'd like you now to tell me, reading off this problem, what is the molarity of our sodium hydroxide? What is the molarity of our sodium hydroxide? What's the concentration of our sodium hydroxide solution? Just reading through the word problem given. 1 molar, exactly right. Okay, let's keep going. What is the volume of sodium hydroxide? What is the volume of sodium hydroxide? 20 milliliters. Okay, and what is the volume of acid? What is the volume of acid? 60. Times 1/1. And if we punch this into our calculator, we get 0.33 that we round to 0.3 molar. So did anything really change in that calculation? Does this look like something we've done before? Does this look very familiar? Does this look like something that we've done before when we dealt with strong acid, strong base calculations? Yeah. So that's what I want you to focus on. Just pay attention to the stoichiometry more than anything. Now we're going to address polyprotic acids and bases. Poly meaning many. So polyprotic acids can donate multi-equivalents of H+, such as sulfuric acid, carbonic acid. So as we notice, we have 2 H+ equivalents from carbonic acid. So in turn, we need 2 OH equivalents. Polyprotic bases, in contrast, can accept multiple equivalents of H+. So you notice how calcium hydroxide has 2 hydroxide equivalents. And as a result, we need 2 H+ equivalents. Now, the key feature of this whole idea of polyprotic acids and bases is the stoichiometry changes. This is why you can't use M1V1 and just call it a day. That's why I've always been drawing out that stoichiometric ratio, because it's critical. Okay. So, an interesting feature of titration curves for polyprotic acids and bases, since there are 2 protons, there are 2 equivalence points, half equivalence points, and buffer regions. So this represents for our proton number 1, and this represents the endpoint for proton number 2. So would someone like to tell me what's the major species for this titration of carbonic acid after we remove our first proton? What do we call that species after we remove our first proton? What's its formula? What is the formula of carbonic acid when we've removed a proton? What's the formula of carbonic acid with 1 less proton? So 2 less would be up here. So yes, you're right that we make carbonate. Oh, whoops, this is oxalic acid, sorry. So it'd be C2O4, 2 minus. And then after proton 1, we'd have hydrogen oxalate, which is H2C2O4, 2 minus. Let's talk about now the different regions. So the first equivalence point is the region where the acid and base are present in a 1-to-1 stoichiometric ratio or in a stoichiometric ratio needed to remove the first proton. So here we're making sodium hydrogen oxalate. In our second equivalence point, it's the region where the acid and base are present in stoichiometric amounts or in a stoichiometric ratio to remove the second proton. So in this case, we have a 1-to-2 ratio. So what's really important to keep in mind, is that you account for the stoichiometric ratio in your calculations. So let's show an example problem. Let's show an example problem where we titrate a polyprotic acid. So let's suppose we have a 20 milliliter sample of oxalic acid, and we needed 20 milliliters of NaOH to reach the endpoint. And we're asked to calculate the concentration of the oxalic acid solution. Okay. Let's zoom in just a little bit. Okay, so we know at the equivalence point that the moles of oxalic acid are equal to the moles of sodium hydroxide. And now my question to you is, how many moles of oxalic acid do we need to react completely per mole of sodium hydroxide? What is our mole to mole ratio? 1 to 2, exactly right. And this is something you can't miss because this is the only gimmick for our polyprotic acid titrations. So then we plug in and we have our molarity of acid times the volume of acid is equal to the molarity of NaOH times the volume of NaOH times 1/2. And this is really critical. Okay, now all we have to do is solve for the molarity of our acid. So the molarity of our oxalic acid is equal to the molarity of our NaOH times the volume of NaOH over the volume of acid times 1/2. Now all we have to do is substitute, and we get the molarity of oxalic acid is equal to 0.5 molar times 20 milliliters over 20 milliliters times 1/2. And that in turn, one moment. And that in turn would give us 0.25 molar. Give me 1 second to restart OneNote. Any questions so far? I apologize for the technical delay. OneNote is back up and running. Allow me to reshare that screen. So after we punch this into the calculator, we get 0.25 molar for our concentration of oxalic acid. Does that make sense to everyone? The only thing that changes is this 1/2 term.